Hi, hello everyone. Good evening all of you. I hope I am perfectly audible and visible to each and everyone present over here. How's everybody doing? I hope all are doing well. Anyway, a warm welcome all of you to the YouTube channel of Infinity Learn by Sri Chaitanya. It's me Surya, your chemistry mentor for this particular session. Okay, in the last session we have covered the third part of this particular chapter, right? Classification of elements and periodicity in properties. And we have covered through the periodicity in properties just like that, atomic radii and metallic and non-metallic character, right? In this particular session we are dealing with the topics like ionization enthalpy, their periodic trends, as well as electron gain enthalpy in their periodic trends in the periodic table, right? Hi, hello, good evening. Okay, without wasting any time, let's directly go to the topic, that is the ionization enthalpy. Okay, what do you mean by an ionization enthalpy? Any guess? Hi, I am going well. What about you? Okay, what do you mean by an ionization enthalpy? Actually, it is the term related to an energy. It means that the minimum energy required to, okay, this is the minimum energy required to remove electron from an isolated gaseous atom, right? In an isolated gaseous atom, it is the energy required to remove an electron from the isolated gaseous atom to form its cation or the gaseous ion, right? That type of energy is known as the ionization energy. As you can see here, if I am taking an isolated gaseous atom M here, by absorbing an amount of energy IE known as the ionization energy, it will form the cation, right? It will form its cation or the respective gaseous ion by releasing one electron using ionization energy. The term is known as the ionization energy. And I also already mentioned that. Okay, you are a 8th student, right? Then also you studying from the channel. Yeah, great. Good. Okay, in the case of an ionization energy, in order to remove an electron from the gaseous atom, we are just giving the energy to the atom, right? Which means the energy given is always positive, right? Energy is always required to remove the electrons from an atom. Hence, the ionization energy delta H is always positive, right? It is always positive. Clear? Is it clear? Now, let us move to the classification of this ionization energy, or it is again known as the ionization potential. Whether, depending upon the energy, it is again classified into two types. First one is first ionization enthalpy. What do you mean by the first ionization enthalpy? It is similar to the same ionization enthalpy in which the energy required to remove the most loosely bound electron from their neutral gaseous atom, right? Energy required to remove the electron from a isolated neutral gaseous atom, or simply we can say that it is same as that the ionization enthalpy. Same here, right? Metal atom, when it is absorbing the energy, it will form M plus ion by releasing one electron, same as that the ionization enthalpy. Then again it is known as first ionization potential or ionization, simply ionization potential, and it is denoted by IE1. Otherwise, we can say that, as you can see here, right, by absorbing the energy, it will form its unipositive ion, which means only one positive charge, right? It will form the unipositive ion. Similarly, if you are adding more energy to a unipositive ion, it will again release one more electron, right? Then it will form a dipositive ion. As you can see here, if I am taking a M plus ion, right, this is the unipositive ion. While giving a particular energy to that, it will form the dipositive ion, right? Dipositive ion. This particular energy is known as the second ionization enthalpy or second ionization potential. Is it clear? Hi Kabil, good evening. Is it clear? We have already seen about the ionization enthalpy. Then the ionization enthalpy is divided into two types depending upon their formation of charged ions. If it is forming a unipositive ion, the energy is simply known as the first ionization energy or first ionization potential. Whenever we are again removing one more electron from the unipositive ion, it will again absorbing the energy, right? Then it will form a dipositive ion known as the second ionization potential or second ionization energy. Clear? Now, let us see the trends or the factors that affect the magnitude of ionization energy. As you can see here, there are 5 factors like nuclear charge, atomic radii, straining effect, electronic configuration and net charge on the ion, right? Let us see the effect of these factors in detail. The next slide. Okay, the first thing is the nuclear charge, right? As you can see here, as the nuclear charge increases, ionization energy also increases. Okay, in the previous class we have already discussed about nuclear charge, right? What do you mean by nuclear charge? What do you mean by nuclear charge? Simply it will be the charge of nucleus, right? Which means it will be the number of protons. The number of protons. As the nuclear charge increases or the number of protons increases, which means there will be a strong attraction, right? As the atomic number increases, there will be the charge on the nucleus increases, which means ionization energy increases as the nuclear charge increases. Clear? If the nuclear charge increases or the number of protons increases, there will be the strong attraction, right? Okay, there will be the strong attraction, which means we need more energy to release one electron from the particular atom, right? That is ionization energy increases. Otherwise, we can say that the nuclear charge is directly proportional to the ionization energy. Clear? Now, let me move to the next factor that affecting the ionization energy, that is the atomic radii. In the previous class, we have already discussed about the atomic radii in detail, right? What is the atomic radii? It is the distance between the outermost electron to the nucleus, right? That is the atomic radii. Or you can say that as the atomic radii increases, the ionization energy decreases. There will be an inversely proportional relationship, right? If you am taking directly proportional here, it is taken as 1 by atomic radii, right? Which means as the atomic radii increases, ionization energy decreases and vice versa. Clear? What will be the reason behind that? Whenever the atomic radii increases, ionization energy decreases. What will be the reason? Any guess? Okay, as the size increases mean there will be, if I am taking here, for example, if it will be the nucleus and this will be the electron, right? Here will be the electron. Okay, here will be the electron. If I am taking another atom, right? Okay, as the size of the atom increases, there will be the number of shells increases, right? Which means that as the number of shells increases, the attraction between this electron and the nucleus will be very less, right? There will be very less attraction between them, which means that it can easily remove the electron easily, right? There is no need of more energy to release this electron from the valence shell, right? Clear? Which means as the atomic radii increases, ionization energy decreases, right? This is the same thing I have written over here. As the number of shells increases, the distance between the outer electron and the nucleus increases, right? The attractive force between the nucleus and the outer electron decreases. Therefore, ionization potential or ionization energy is inversely proportional to the atomic radius. Clear? Is the things clear? There is no need of any motivation, right? If you have any exams, just study hard for that. Don't take too much stress or don't take too much to depression, right? Like that. Prepare well for the examination. Keep on revising the topics, right? Once you cover all the topics, just keep revising. Don't take too much stress for the exams, right? Okay, I hope it is clear for everyone. Now let me move to the next effect, that is known as the screening effect. We have already discussed, right? I have already given a brief idea about the screening effect in the last class. What do you mean by the screening effect? For example, if I am taking the same, this is the nuclei, this is the atom, right? This is the electron revolving around here. Okay, this is the electron revolving around here. If I am taking another atom, if I am taking another atom here, as you can see here, these are two electrons. Because of the presence of these two electrons, there will be a screening of these electrons from this outermost electron feels a screening or shielding. This outermost electron feels it screening or shielding because of this inner electron from the nucleus, right? From the nucleus there will be a shielding. That is why there will be very less attraction. Right? Which means that there will be very less attraction. We can easily remove the last electron from the valence shell, right? Which means that as the screening effect increases, ionization energy decreases. Right? Clear? As the screening effect increases, ionization energy decreases. There will be the inversely proportional relationship. Right? And this point you have to remember that according to the orbital, there will be the screening effect order. If you are taking S, P, D and F orbital, there will be the order like that. S has the more screening than the P, than the D, than the F, right? This should be important. Clear? Fine. Now I am moving to the next factor that depends on the ionization energy, that is the electronic configuration. For example, if I am taking any noble gas or other elements, it seems that sometimes the subshells are already filled with half filled or completely filled. Right? If it is completely filled or half filled, there will be a high extra stability, right? In order to remove the electron from the high stable atom or element, it will require more energy, right? As I already mentioned here, the subshells with exactly half filled or completely filled with electrons are symmetrical, right? Atoms with the symmetrical orbitals are stable. Therefore, greater amount of energy is required to remove an electron from such a stable atom, right? For example, in the case of all the inert gases or noble gases, for example, if I am taking neon, this is the electronic configuration, right? 1s2, 2s2, 2p6. Neon is having atomic number of 10, which means that this is completely filled, this is highly stable. In order to remove this one electron from the p orbital, no, we need more energy to remove this electron. Clear? Now let me move to the last factor that affecting on the ionization enthalpy, that is the net positive charge on the atom, right? Net charge on the ion or net positive charge on the ion. Thus, with an increase in the positive charge on the ion, the energy required to remove the electron also increases, right? For example, if I am taking an example here, This is our nuclei, then 2 electron is present here, then 1 electron, right? If we are removing this 1 electron from the element, it will form I am removing 1 electron by using ionization energy. It will form this ion, right? Here I am taking the lithium ion and it will form lithium plus ion, right? In order to remove this electron from this now, it will take more energy, right? It is already stable, 2s2 configuration, right? Sorry, 1s2 configuration. It is more stable. In order to remove these electrons from the particular energy level, we need more energy then, right? Then only it will form like this. More energy required, which means that as the positive charge increases, magnitude of the positive charge increases, the ionization potential or energy is also increases. Is it clear? Is it clear? Just let me know. Okay. So far we have discussed the factors affecting on the ionization energy. Now let me move to the periodic trend of the ionization energy in a particular period table along with the period as well as group, right? Okay, what will be the variation of ionization potential energy along a group, that is from top to bottom? What will be the trend? These are some examples I have given here. This is the group elements, that is hydrogen, lithium, sodium, potassium and rubidium. That is the first group elements, right? In the case of first group elements, as you can see here, the ionization potential energy is always decreases. Down the group it decreases, right? Down the group it decreases. Okay, these are the major unit of the ionization potential. You can either express in the kilojoule per mole or electron volt per atom. As you can see here, the electron ionization potential or ionization energy is always decreases down the group. That is from hydrogen to lithium to sodium to potassium to rubidium to cesium. It will decreases, right? Which means that along a group from top to bottom, the ionization energy is always decreases. What will be the reason? Just connect with the factors we have studied. You can start with the radii or the screening effect or anything. Or I can say that down the group number of shells increases, right? Which means size already increases. There will be the very less attraction between the outermost electron to the nuclei. Therefore, it is very less attraction. It is very easy to remove these electrons from the valence electron. So that we can say that there is only small energy required to remove the electron, right? That is why the ionization potential energy gradually decreases along a group. And this is a graphical representation given here. This is from lithium. Lithium started from 520, then sodium, then potassium, rubidium, cesium. This is the general trend in which the ionization energy is decreases in a group. Clear? Okay, there is a weightage percentage of 56% around from this chapter. Main about 4 or 5 marks will be given in the exam. And also from this particular topic, you will get more questions, right? This is very easy chapter, but it is very important. Some memory based questions will be come from this topic for the exams. Piyush, clear? Okay. This is the trend of trend of ionization potential along a group. Now let me move to the trend in a period, right? What will happen whenever we go from left to right in a period? What will happen from left to right in a period? from left to right in a period, ionization potential or energy is always gradually increases, right? Yes, gradually increases. As you can see here in this particular graph, the energy is always increases, right? There will be a gradual increase of the energy from left to right in a period. Left to right in a period, right? What will be the reason? You can just connect with the atomic radii, right? As we move from left to right in a period, size decreases or increases. What will happen for the size? We have already discussed, right? Yes. Atomic radii decreases from left to right in a period, right? Yes. Okay. As we move along the period from left to right in a period, size decreases, right? Which means whenever size decreases, means there will be very less attraction, right? Sorry, there will be a strong attraction, right? If the size decreases, there will be a strong attraction, which means we need more energy to remove the last electron from the valence electron, right? Valence shell. Yes. We can say according to atomic radii also, and also the effective nuclear charge, right? Here you can see that the nuclear charge also increases. As we move across the period, the nuclear charge also increases, but the electrons are always added to the same shell, right? Then also the distance between the nucleus and the outer electron decreases, which means there will be a strong attraction. In order to remove the last electron from the valence shell, we will require more energy, which means ionization energy increases along a period. Clear? Is it clear? Yes. And that was the general trend. Again, there will be some exceptions, right? Some anomalous pairs are present over here. Here you can see in this particular graph, as we already studied that from left to right in a period, there will be the gradual increase, right? It should be the gradual increase. There should be a gradual increase, which means that the graph goes like this, right? Graph should be goes like this, the straight line. But as you can see here, there will be some difference. There should be some difference. From here, that is about beryllium to boron. What will happen here in the case of beryllium to boron? According to our general trend, it should be increases, right? From beryllium to boron, there should be an increase in the ionization energy. But here you can see that beryllium has a more ionization energy than the boron. There will be some special reason. Similarly, you can see here in the case of nitrogen and oxygen, nitrogen has more ionization energy than the oxygen, right? What will be the reason? Okay, I have already mentioned about the electronic configuration, right? If the atom or element having the half-filled or completely filled electronic configuration, it must be stable, right? In order to remove the electron from the stable electronic configuration, we need more energy, right? We need more energy. For example, if I am taking beryllium here, 1s2, 2s2, right? This is the completely filled electronic configuration. As the beryllium atom contains completely filled outer s orbital, it has a greater stability. Moreover, the s orbital, there will be one more factor affecting the ionization energy, that is penetrating power, right? It is the penetrating power of the orbital. As you can say here, the penetrating power or penetration power of orbitals. It is always greater than for S, than P, than D, than F. This will be the order of penetration power of the orbitals. Noted. Moreover, in the case of beryllium, the s orbital has greater penetrating power. Hence, energy required to remove electron from the beryllium atom is high. Right? Is it clear? That's why beryllium has a greater ionization energy than that of the boron. Clear? Similarly, in the case of nitrogen and oxygen also, in the case of nitrogen, that nitrogen is greater than that of oxygen, because whenever we are writing the electronic configuration of nitrogen, we can say that 1s2, 2s2, 2p3. 2p3 means this is a half-filled configuration, right? Half-filled configuration. Again, it has the extra stability. Again, it has the extra stability. So, in order to remove the electron from the valence shell, we need more energy, right? That's why energy required to remove electron from nitrogen is very high as compared to oxygen. Clear? Okay, now let us practice some questions based on this topic. Here is the first question for you. Some of the elements are having outermost electronic configurations are given here. You have to find out the correct order of first ionization enthalpy for them. For the first element A, its electronic configuration is 3s2, and for B it is 3s2 3p1, for C it is 3s2 3p3, for D it is 3s2 3p4. Identify the correct order of first ionization enthalpy for these four elements A, B, C and D. What will be the answer? No answers. Options are already given here. You can just guess the answers. Whether it is A, B, C or D. Okay, fine. Just give me the idea how we can approach this question. Hi, Pram. How we can approach this question? Electronic configuration is already given, right? For example, I am taking here A, it is 3s2. Then B, it is 3s2 3p1, right? C, it is 3s2 3p3. And for D, it is 3s2 3p4. Which means that these all the elements are belong to the same period, right? Same period. That is in the third period, right? Then what will be the expected trend here? From left to right in a period, what will happen? General trend. From left to right, what will happen for the ionization potential or ionization energy? Right? This will be the general expected trend because from left to right in a period, size increases, right? Sorry, size decreases, which means ionization energy increases. This will be the general trend of size, that is already it is increases from A, B, C, D. Then as you can see here, we have to identify the electronic configuration, right? This is the half-filled electronic configuration, right? This will be the half-filled electronic configuration. And this will be the full-filled electronic configuration, right? So according to the half-filled or full-filled configuration, we can say that in which one have the maximum ionization potential here compared to A and B? compared to A and B. Which one have the maximum ionization potential? B, right? Because A have the highest. B, A, D, C, because A have the more stability, right? Because of the fully filled electronic configuration, therefore more energy is required than the B. Therefore B, A. Then as compared to C and D, which one have the more energy required to remove the electron? C, right? C have the half-filled electronic configuration. Because of the highest stability, we will require more energy to remove the electron, right? From here C to D, D had the more energy than the C, right? Which means option B will be the correct answer here. B, A, D, C. Yes, option B will be the correct answer here. Clear? Clear? Here is the next question for you. Again, the first ionization enthalpies of beryllium, boron, nitrogen and oxygen follow the order. This is a question came from the JEE Main shift to 2022 July 25. What will be the answer? These are the anomalous pairs, right? Oxygen and nitrogen. Again, beryllium and boron. We have already discussed. Yeah, C and D. Okay, what about others? Yes, option D is the correct answer. What will be the expected trend we are expecting? Because beryllium 4, right? Boron 5, nitrogen 7 and oxygen 8, right? This will along the same period. As along a period, what will happen to the ionization energy? Ionization energy increases, right? Ionization energy increases, which means that we are expecting this trend. Beryllium has maximum, beryllium has less than that of the boron, then nitrogen, then oxygen, right? This will be our expected trend, right? Expected order. But what happened here? Because of the stable electronic configuration, right? Because of the stable electronic configuration, we can say that in the case of beryllium, it is the full-filled electronic configuration, right? Full-filled electronic configuration. Because of this extra stability, it will require more energy to remove the electron, which means B less than B. Then according to the nitrogen and oxygen, nitrogen has the half-filled electronic configuration, right? Half-filled electronic configuration. Again, it gets this more stability. In order to remove the electron from the nitrogen atom, we will require more energy than the oxygen, right? Therefore, this will be the correct order for the ionization enthalpy for these particular elements, which means option D will be the correct answer. Clear? Yes, incorrect, because half-filled and fully filled orbital. Clear? Now, let me move to the next topic, that is the next periodic property trend, that is the electron gain enthalpy. What will be the electron gain enthalpy? Any guess? Similarly, this is also the energy change or enthalpy change, right? That is, it is the enthalpy change happened whenever an extra electron is added to the neutral isolated gaseous atom, right? Whenever an extra electron is added to the neutral isolated atom, there will happen some energy changes, whether it is positive or negative. That will happen. That type of energy or the enthalpy is known as the electron gain enthalpy. While gaining the electron, it requires some energy, whether it is absorbing or releasing. That type of energy is known as electron gain enthalpy, and it is represented by delta Hg. This is the representation of enthalpy, and Eg represents the electron gain. Clear? Similarly, it also has the unit kilojoule per mole or kilocalorie per mole, right? Then again, this electron gain enthalpy is divided into two types, whether it is positive or negative. For example, if I am taking a negative electron gain enthalpy, which means that the release of energy, if there is an energy is releasing, there will be the exothermic, right? Energy is releasing, which means that it has a negative value of enthalpy. The release of energy in the electron gain process is represented by the negative electron gain enthalpy or negative delta Heg. For example, in the case of halogens, what will be the case of halogens? Yes, and it's clear. Electron affinity and electron gain enthalpy means it almost has a similar value, but it is a different in their signs. We are taking electron affinity in the negative sign only, and almost all the time, what will happen? The electron gain enthalpy and electron affinity have the same magnitude, right? We will discuss it in the detail in the next session, right? Clear? We are going to discuss the electron affinity detail in the next session. Is it clear now? What will be the difference? Okay, for example, if I am taking the halogens, what will be the halogens? For example, fluorine, right? Fluorine have the electronic configuration of 2,7, which means, yes, group 17, right? Group 17 means halogens. In the case of halogens, it is 2,7 electronic configuration. For example, in the case of fluorine, if you are having the 2,7 electronic configuration, it needs one more energy, right? One more electron to get the octet configuration, right? Which means that energy is used here, or energy is releasing here to get the one electron, which means that it will have the negative value of energy. Clear? Clear? Now let me talk about the positive electron gain enthalpy. If some of the elements do not willing, if they are unwilling or reluctant to add the electron, then more energy is given here, right? Energy is given to that, which means energy is absorbing here. That type of energy is known as the positive electron gain enthalpy. For example, in the case of noble gases, right? I will write here. For example, if I am taking neon, right? This will be the electronic configuration of neon, which means 2,8, it already completed the octet configuration, right? It is already in a stable condition. It is already in a stable condition because it has the complete octet configuration. There is no need of more electron, right? There is no need of more electron, but we have to add electron to that, which means we are adding more energy to that. It will have the positive electron gain enthalpy. Clear? Similarly, in the case of alkaline earth metals also, for example, magnesium, right? Magnesium 282, it is the completely filled configuration having the stability. In order to require one more electron to add the Mg atom or element, it will require more energy, that is the positive electron gain enthalpy, right? These are the examples, noble gases as well as the alkaline earth metals. It shows the not positive, it shows the negative electron gain enthalpy. Sorry, the positive electron gain enthalpy. Clear? And this will be the general representation of electron gain enthalpy, which means that this X will be our isolated gaseous atom. Whenever we are adding more electron to that, it will forming a negative ion or anion by changing the electron gain enthalpy, that is the delta Heg. Clear? How to check if a reaction is endothermic in nature or not? If you are given the value of delta H, right, according to electron gain enthalpy or delta H value, if it is given as positive, for example, wait, I will write here. Okay, I will write here. If the delta H value is positive, right, which means the energy is always absorbing. Energy is absorbing. Okay, energy is absorbing here. In this particular case, we can say that this process is endothermic, right? This process is endothermic, right? And just opposite to that, if the delta H value is negative, which means that energy is releasing, then the process will be exothermic. Then the process will be exothermic. Yasin, it's clear? Is it clear now? Now we are talking about the factors influencing the electron gain enthalpy, right? As you can see here, these are the main factors that is affecting the electron gain enthalpy. First one is the atomic size. There will be an inversely proportional relation between atomic size and the electron gain enthalpy, which means that, yes, which means that as the atomic size increases, the electron gain enthalpy decreases, right? Similarly, if the nuclear charge decreases, the ionization enthalpy decreases. There is a directly proportional relationship. And also when we are considering the screening effect, as the screening effect increases, the electron gain enthalpy decreases, right? Clear? Is it clear? These are the factors affecting the electron gain enthalpy. As I already mentioned about the atomic size in detail in the previous classes. Similarly, nuclear charge and screening effect I already discussed. According to these factors, we can define the magnitude or the change in electron gain enthalpy along a period as well as group, right? Let us see the trend in a group as well as period. What will happen in the case of a group while moving from top to bottom? While moving from top to bottom in a group, size increases, right? So that the electron gain enthalpy decreases due to the inversely proportional relationship. Electron gain enthalpy decreases along a group from top to bottom. And the reason is given here. On going down the group, the atomic radius and nuclear charge increases. Atomic radius and nuclear charge increases. With an increase in the radius, attraction of the added electron by the nucleus decreases. Attraction of the added electron by the nucleus decreases and the electron gain enthalpy decreases. Is it clear? Whenever we are moving down the group, size increases, right? As the size increases, there will be the very less attraction between the added electron to the nucleus. Therefore, the electron gain enthalpy decreases. Clear? Similarly, what will happen along a period from left to right? The electron gain enthalpy gradually increases, right? Gradually increases along a period from left to right. The reason is given that on moving across the period, atomic number increases, right? Atomic number increases or the size increases as the nuclear charge increases and the radius decreases. Atomic number increases, the nuclear charge also increases, but the size decreases along a period from left to right. Because of these reasons, the attraction between the added electron, and the nucleus increases. Size decreases, right? For example, this will be our nucleus. This will be one atom having the, or one element having the small size, right? Small size, which means whenever we are adding one electron to this particular element, because of the small size, there will be a strong attraction between them. Therefore, the electron gain enthalpy increases. The electron gain enthalpy increases along a period from left to right. Clear? Again, here also we can see some anomalous pairs. In general, in a group, what will happen? The electron gain enthalpy will be changes, right? But if I am taking the example of fluorine and chlorine, you will see that fluorine is less negative electron gain enthalpy than that of the chlorine. It will, okay, in the case of a group, electron gain enthalpy should be decreases, right? In the case of a group from fluorine to chlorine, electron gain enthalpy should decreases. But you can see that the electron gain enthalpy of fluorine is less as compared to that of chlorine. What is the reason behind that? This is the electronic configuration of fluorine and chlorine, right? Whenever we are adding one electron to the fluorine atom now, it is always added to the second shell. N is equal to 2 quantum level, and it suffers significant repulsion from the other electrons from this level, right? This is the electronic configuration of fluorine, 1s2 to 2s2, 2p5. If we are adding one electron to the particular atom, it will enter into this 2p orbital, right? There will be more repulsion between the other electrons already present in the 2p orbital. That is why the fluorine experience less negative electron gain enthalpy. Then if you are considering the chlorine atom, right? Chlorine atom means 1s2, 2s2, 2p6, 3s2, 3p5. Again one electron is added to the 3p orbital, which is the third orbital, right? N is equal to 3, third orbital. In the case of third orbital, because of the large area, there will experience a very less repulsion, right? It occupies a larger surface of area or region of space. Therefore, it experiences weaker electron repulsion than the fluorine, right? That is why we are experiencing very less negative electron gain enthalpy for fluorine that of chlorine, right? Clear? Similarly, one more anomalous pair is here, that is oxygen and sulfur. Oxygen and sulfur, right? Okay. This is the particular values of electron gain enthalpy for particular element here. And as you can see here, in the case of, these are the inert gases, right? Inert gases or noble gases. Helium, neon, argon, krypton, xenon and radon. As I already mentioned that in the case of inert gases or noble gases, it has a stable octet configuration, right? It is already stable. In order to add one more electron to the particular element, we need more energy, right? That is why this electron gain enthalpy is always showing positive value, right? Plus 48, plus 116, plus 96. Again, this is the point you have to note that almost similar value for the argon and krypton, plus 96. Similarly, in the case of xenon and radon, it is positive value, right? Clear? Then, this is the anomalous pair, right? Fluorine and chlorine. While moving down the group, what will happen to the electron gain enthalpy? It should be decreases, right? From fluorine to chlorine to bromine to iodine to astatine, it should be decreases. But this is the anomalous behavior of fluorine to that of chlorine. As I already mentioned that fluorine has a less negative electron gain enthalpy than the chlorine, right? This should be noted. This is the important point. More questions will be coming in your exams. Similarly, in the case of oxygen and sulfur, sulfur experiences more electron gain enthalpy, the negative value, than the oxygen. Same that of the anomalous pair, right? And this is the general trend here: nitrogen and phosphorus, carbon, silicon, boron, aluminium, beryllium, magnesium. And you can see that in the case of beryllium and magnesium, it shows positive electron gain enthalpy. What will be the reason? It shows positive electron gain enthalpy. What will be the reason? Anyone? In the case of beryllium and magnesium. Okay, beryllium and magnesium has the alkaline earth metals, right? Alkaline earth metals. It has a stable electronic configuration of completely filled s2 orbital, right? Alkaline earth metals. If I am saying here, this is 1s2, 2s2, it is already stable because of the completely filled electronic configuration. In order to add one more electron to the particular atom, we need particular atom or element, we need more energy, right? That's why these value getting positive electron gain enthalpy values, right? Clear? And there is one more point you have to note that in the case of nitrogen, because of the half filled orbital, it also shows positive electron gain enthalpy, right? Clear? Is the things clear? Now let us practice some questions based on the topic. Which set of elements shows positive electron gain enthalpy? Three set of elements are given here. You have to identify the set of elements which shows positive electron gain enthalpy. What will be the answer? No answers? Generally, the positive electron gain enthalpy are shown by the inert gases, right? Inert gases. So, you have to just identify what are the inert gases. If the set of pairs, set of three elements given as the inert gases or not. As you can see here, helium and neon is inert gases, right? Helium and neon is inert gases because of the complete electronic configuration. Then we have already known that in the case of nitrogen, because of the half-filled electronic configuration, it will experience more stability, right? That is why we need more electron gain enthalpy to add one more electron to the nitrogen atom, which means that these set of elements like nitrogen, helium and neon have the positive electron gain enthalpy. Clear? That is option D will be the correct answer here. Here is the next question for you. In general, the property in magnitudes only that shows an opposite trend in comparison to the other properties across a period. Options are given here: ionization enthalpy, electronegativity, electron gain enthalpy and atomic radius. We have already covered the ionization enthalpy, electron gain enthalpy and atomic radii in detail. Then electronegativity we will discuss in the next class. What will be the general trend? What will be the only one property that shows opposite trend in comparison to other properties across a period? What will be the answer? Option D, right? Atomic radii. As you can see that in this particular image, while moving from left to right in a period, electron gain enthalpy increases, right? This electron gain enthalpy always increases along a period. Then what will happen to the ionization enthalpy? It also increases, right? Ionization enthalpy also increases along a period from left to right. Ionization enthalpy increases, electron gain enthalpy increases. Then we have already discussed about the atomic radii, right? Atomic radii is always, what will happen to the atomic radii? From left to right in a period, atomic radius decreases. Atomic radii decreases. Then I will give a brief idea about the electronegativity. As you can see here, the electronegativity increases along a period from left to right. We will discuss on later in detail. Increases, right? Which means that among these four properties, we can say that only one property is atomic radii that shows opposite trend that of the all other three properties along a period. Clear? Again, option D will be the correct answer here. Is the things clear? Okay, this is all from my side for today. I hope it was clear for everyone. If you have any doubt, you can ask now. Otherwise, we can wind up the session for today. So far, we have discussed the four properties, right? Starting from the atomic radii, then the non-metallic and metallic character. Then now, ionization enthalpy as well as the electron enthalpy trends along a period as well as group in a particular periodic table, right? On the next session onwards, we will discuss about the electron affinity as well as electron positivity or electron affinity as well as electronegativity in detail. Clear? Okay, do like, share the particular session to your friends and subscribe our YouTube channel for more details. Anyway, thank you so much. Bye bye. Take care. Good night all of you.